All right, I think this will be the last Navier Stokes video. In it, we're gonna derive the Poisson equation, and then also get equations that you can put in MATLAB and simulate fluid flow, which is pretty sick. I probably won't derive all of them, but I'll give you the tools you need to derive them, just because there's a lot of numbers and a bunch of places to mess up algebra, and it's kind of a waste of my time. Okay, but the Poisson stuff is pretty interesting. So the idea is we want to find an equation for pressure, because we don't directly have it. We have the Navier-Stokes and we have the continuity, and we've shown that we can calculate the velocity profiles and that sort of stuff, but like finding an equation for pressure, it's a little complicated. And finding a general equation for pressure is even more complicated, but that is what we're doing, and it's a pretty nice approach. I only found one guy on YouTube who did it this way, so I'm kind of copying what he did because it makes sense and it's a great way to do it. But yeah, so we start with continuity. We're going to assume it's two-dimensional. So we're going to drop all terms that have U or W and all terms that have a dz. So du dx plus dv dy equals 0. All right, now let's write out the Navier-Stokes. So what's a nice way to do it? Let's do it this way. Navier-Stokes in X. We don't need that because we're just doing 2D. And let's assume there's no gravity, so that would go away. So dp dx. Okay. Cool. Just to match what I have in my notes, I am going to add a 1 over rho there, and this over rho here. So it divided everything by rho. Yep. Yep, we got V's here. And V, V. Okay, I think that looks good. So, next, we're going to take the derivative with respect to x of the Navier-Stokes x equation. And that will equal, dang it, I'll do it below. Maybe I should have formatted it better from the start, but 2 dt plus, if we apply it here, we'll have dx of u, du dx. So we have to do the chain rule. So that'll be du dx, du dx plus u d squared u dx squared. Is that right? Yep. Okay. And this can just be rewritten as du dx squared. Okay. Next, we have the same thing over here. D dx, v du dy. And this one's kind of weird, but we do it. V dx du dy plus v d squared u dy squared. No, dx dy. Okay. And then we have the right-hand side. And the right-hand side is that d squared p dx squared plus this over that times, yeah, just cubes. Okay. Yep, we're good there. Okay. Same thing, but for the y. So I have d dt plus u, well, it would be du dx dv dx du dy dv dx, yep, plus u d squared v over dx dy, is that right? Yep, plus this would be dv dy squared plus v d squared v over dy squared. Yep, equals 1 over rho squared plus cubed. Okay. Very cool. And now we add them. Yep. All right, so we add left, I'll break it into the left-hand side and right-hand side. So that's left-hand side, that's left-hand side. Yeah. Oh. Yep, okay. Yeah, it's pretty brutal. There are simplifications, but we have to write it all out first, which really sucks. So, well, let's start by grouping a couple terms. And let me actually rewrite these as well. du dx dt dv dy dt. Okay, so now let's group them. We can group these two by pulling out a dt. So d over dt du dx plus dv dy. Okay. And anything else yet? No, not really. I'll do these two squared terms. Squared plus dv dy squared. Okay. There's two of these terms. So let's say two of those plus 2 dx. Okay. Plus, there's two terms with a u in front. So let's group those. D squared u dx squared. D squared v over dx dy. And there's two terms with v in front. So let's group those. D squared u dx dy plus d squared v dy squared. All right, this part's gonna be really cool. I'm a freaking nerd for saying that, but it's pretty cool. All right, so we have the continuity. Du dx plus dv dy equals 0. 0. This can be rewritten as, I don't even need the arrow. This can be rewritten as d dx will be u d dx of du dx plus dv dy. That goes to 0. And then this one can be v d dy du dx plus dv dy. That goes to 0. Like, this is freaking sick. The guy on YouTube is a great guy. So this whole thing simplifies to du dx squared plus dv dy squared plus 2v dx du dy. That is, that's the left-hand side. Okay. Now the right-hand side. Yeah, okay. So let's start by grouping those two. Yep. And then we will write out the rest of them, but group them. What order do I want to write them? I want to write them in this order. Probably see where this is going. Same exact thing as above. These two terms. That's a terrible arrow. Can be expanded as d dx squared du dx plus dv dy. That goes to 0. Continuity. Same with these terms. D dy squared du dx plus dv dy. That goes to 0. So we're left with just this part. So then we have our complete equation when we write it out. We have du dx, it's terrible, squared plus dv dy squared 2 dv dx du dy equals 1 over density cool. And that is literally it. Some places that I've seen refer to this term as b. Mainly I've seen it in code. And the reason is if you code this whole thing out, this whole equation out, it's freaking long. It's very long. So they separate it into two things and they just call it b. You can call it whatever you want. You can call it like, don't call it x because x is a variable. You can call it like m, or you can call it whatever you want. But yeah, this is literally it. So that's that. Okay. So there are a couple definitions when, well, okay, if you want to code this stuff in MATLAB, you need a couple equations. You need this equation, you need this equation, you need Navier-Stokes X and Navier-Stokes Y. You need those three equations. You need to code them in MATLAB, and it freaking sucks. And the reason why it sucks is because you have to use numerical approximations, which they make sense, but they're dog water. All right, so what types of things do we have? We have a d, let's say u dt. We have a du dx. You can replace the u's with the v's. And we have d squared u dx squared, because we have squares there. And we have derivative with respect to time, x square again, time x or y and square. It's the same formula. For x or y or u or v, it's all the same formula. And down here, again, we have single derivatives, and we have double derivatives. So that's it. So let's start with this one. du dx. So if you're writing it in code, can I? Yeah, okay. I'll use these dots, actually. It's very nice. So they call it a stencil, but you can call it whatever you want. So you got these dots. Let's just say you have a grid of them, right? Let's say you want to find the derivative at that middle point. Well, what is the derivative? The derivative, if you have like a normal graph, and you got like a line or whatever, derivative between those 2 points, you would subtract them. So it would be y2, y1, x2, x1. So it would be y2 minus y1, x2 minus x1. And that is the derivative. I don't even know what to write for the equals, but that is the derivative. So it's the exact same idea here. So to find the derivative of this point, let's say with respect to x, and x is that way and y is that way. It would be the value at this point minus the value at that point divided by the distance between them. So let's say your grid is, let's say it's like, what would it be? You specify it, so you can say whatever you want. Let's say it's 1 meter and there's 10 data points. There's 10 grid points in each direction. So let's say your grid is like a cube and it goes from 0 to 1 and 1. And this will be 1 and 1. Let's say you break it up into 10 things. So there's like 10 grid points along there. The distance would be 2 times dx. And dx in this case would be, what would it be? 0.2, because it'll be 10 divided by 1. But yeah, so back down to here. The derivative of u would be u, well, okay, the way I'm going to write it is ij with a comma. So I can denote that this is point I, j, this is point I plus 1, j, this is point I minus 1, j. Up here is I, j plus 1, and I, j minus 1. And the reason that you write it like this is because when you're doing like double for loops or whatever through code, like through MATLAB or Python, it helps indexing it like this. Although people don't like you using double for loops, they just like backslash operators and all that stuff. And I'm like, I don't know, man. I like my for loops. All right, so it would be u at I plus 1, j minus u at I minus 1, j over 2 dx. And you would declare dx like higher in your code. Like let's say L is 1, which it is here. That's the distance. But let's say you have n equals 10. So you make a 10 by 10 grid of data points. Then dx would equal L over n, which equals 1 over 10, which equals 0.1. So you would declare it in your code. Yeah, so that's it. And if you have a du dy, you just replace this with dy, and it's the exact same calculation. assuming yours is a square, if yours is a rectangle, then you would have like a L and a H. And then you have like a H equals like, let's say 2, and then it would be dy is 2 over 10, and that is 0.2. But you get the idea. So that's that one. Now, second derivative, it's not as visual to explain. Well, it kind of is, but I'm not going to do it. The equation is ui plus 1j. Oh, and if you swap to y, I'll just write it out. You have to flip the indexes. So you have to, right, because that makes sense up here. Instead of this distance, you're doing that distance, and you're looking at those 2 points now. So you have to flip the indexes. I'm not even going to write the rest of it out. You get the idea. There's going to be that one person out there who's like, no, write it out. And I'm going to be like, frick you, I'm not writing it out. So minus u at ij, yep, but it's 2 times u at ij. There is math behind it. I don't want to derive it now, partly because I don't have it in my notes, and I don't really want to mess up and spend a lot of time doing it. Plus ui minus 1j over delta x squared. That's the same as dx. Well, technically no, but it's the same. Dx squared. And yeah. So it would be 0.01 if you square it. So that's the first and second derivative. Now, you would think that the du dt should be the same as du dx, and you would be right, except in time, we don't know the future time. So we have to find the future time. So an alternative derivative, if we don't know the points on the left side and the right side, all we know is a point on the left side and the middle point, then we do the best that we can, and we just have those 2 points. So we have the left point and the middle point, and we just do the slope between those two, and that's the best we can do. So that's what we do here. So it would be uij minus ui minus 1j over dt, and we declare a dt, and dt is, there is math behind it. If your time step, your delta time is too big, it will ruin the calcs. If it's too small, it'll take forever to run. So you want to pick one that's good. And there is math behind finding one that's good, and it involves, I think it involves the dx and dy that you calculate. It's like, I don't know, dt equals, it's a function of dx and dy. It's something like that. Something like that, I don't know. But this way, okay, that's the notation I did there is slightly wrong. Let me see. Technically, this whole thing is x and y. T, it would go out of the page in the z direction. So you'd, yeah, so technically this is wrong. So you're doing the same exact thing, but now it's like a face. It's like I don't know what face that is, but anyways, you're doing the same exact math, but now you're doing it on the ij point in the middle. You're doing it on that point, but you're doing it with the next point, which is like into the page, right behind it, but it's the same point. It's ij, but it's the one from the previous time. And you do that with all your arrays and stuff, but it works. So it's the same point, it's ij, but it's from the previous time. So that's it. Now that you have all of these, you plug these into each term, each individual term. So you have all 1, 2, 3. These would be uij and vij. But you have each term and you have to plug it into all of them. So the math, like, it's a super long equation and there's a lot of algebra places to mess up. And you also have to, if it's not bad enough already, you also have to solve for Pij, because that's one of your equations. It's got to be Pij equals something. That's one of the equations you have to have in MATLAB. And you do that by plugging in into those two terms. You plug in these, but you replace u with p, and then it would be p and p. You get the idea. You plug both of them in, and then you solve for these terms. It will be Pij, but you solve for those. It's a lot of algebra, and you can mess up very, very easily. And I've messed up a ton of times to the point where I don't even do it anymore. But yeah, so that's how you solve for the Pij equals something. And it equals all this. So then you have the Pij equation, and you have the two Navier-Stokes equations from up here, and that's 3 unknowns and 3 equations, because the unknowns are P and U and V. So you have 3 unknowns, 3 equations, and you let MATLAB do its thing. Oh, and technically time, but that's what you're time stepping in, so it works out fine. But yeah, that's about it. The part from now on really sucks, and it's just a waste of time for me to do it, because you know what to do. If you've gotten this far, you know how to do algebra. But yeah.